Good morning all of you. What we are going to cover today in this lecture is the structure of the atom, which is extraordinarily important for all the developments in the 20th century, for that matter even in the 21st century. So, the structure of the atom essentially involves first of all an understanding of the classic experiment by Rutherford when he scattered alpha particles of gold nuclei, what we call as gold nuclei today. And then of course, the planetary model which followed from the Rutherford scattering had to be reconciled with spectroscopic data and with the very problem of the stability of the atom, for which Bohr gave his model. So, in other words, what we are going to discuss in the class today is one of the most crucial developments in physics, because after all, if we understand the basic constituents of matter, the rest of it would be a matter of detail, however complicated it may be. As I told you in my last lecture, the concept of de Broglie waves or the matter waves was actually introduced after Bohr gave his model. In fact, many years after Bohr gave his model. So, historically de Broglie was impressed, he was influenced by these special orbits that Bohr had proposed, and he thought that that could correspond to standing waves of matter waves. But that is not the viewpoint that we are taking in this course, just as that is not the viewpoint that is taken in your 12th standard NCERT course. So, I will return to that concept, but we should remember that the structure of the atom precedes the concept of a matter wave. So, in the last lecture what we essentially did was to introduce the concept of matter wave, and we gave an experimental demonstration of this idea. This was a hypothesis which was put forth by de Broglie, but then Davison and Germer, through their ingenious experiments, were actually able to diffract electrons of a nickel crystal. So, we should always remember the famous formula 2d is equal to 2d sin theta is equal to n lambda. So, the scattering angle is governed by this formula. N is the order of diffraction, d is the spacing between the planes of the crystal, lambda is the wavelength. So, the scattering result was consistent with this formula which is valid for waves and not what they expected of electrons as particles. However, we should remember that experiments with cathode rays, or for that matter even E by M measurements, strongly suggest, in fact they provide great evidence that electrons are actually very tiny particles. So, again we have the same dilemma that we encounter, the same duality that we encountered in the case of light. With interference and diffraction it behaves like a wave, and with regarding to photoelectric effect or Compton scattering it behaves like a particle. In a similar manner, electron when it is getting accelerated by voltage, when you are looking at its tracks in a magnetic field, etc., behaves like a particle, but then when it is scattered off a nickel crystal, then it shows beautiful diffraction patterns. So, we have to remember that. Before I go on to discuss the structure of the atom, I want to round off a discussion by cautioning you on how careful we should be in using the concept of wave, especially when it comes to matter wave. So, let me recollect what we have done both in the case of light and in the case of matter. So, let us start with light, electromagnetic radiation. So, in the case of electromagnetic radiation, we have two important expressions, E equal to h nu, and the second expression is obviously given by V equal to c. All wavelengths propagate with the same speed given by, denoted by c, which is 3 into 10 to the power of 8 kilometers per second, and this is nothing but nu lambda. In other words, when we associate an energy with a frequency nu associates an energy E, we are also associating the same energy with a wavelength, because after all my nu is nothing but c by lambda. So, it is entirely a matter of taste whether you want to relate energy to frequency or energy to the wavelength, at least at this particular point, and therefore I can write E is equal to h c by lambda. That is what I have. So, in my lectures on photoelectric effect, I also argued that it follows from classical theory. All this is Planck. So, it is as if we are riding two horses, sometimes that of Maxwell and sometimes that of Planck. Now, if I come back to Maxwell, the age old wave theory, which of course has a great experimental evidence, Maxwell says that if you have a monochromatic plane wave, let us say, then the energy density is related to the momentum density by a factor of c. So, this is energy density and this is momentum density. So, what do I mean by energy density and momentum density? That is the energy per unit volume carried by the radiation, and momentum density is the momentum carried by the radiation per unit volume. That is what we have. Now, Mr. Planck would like to associate a certain number of particles corresponding to this and corresponding to this. So, if you have an energy density corresponding to radiation of a given frequency, so if you want I can put the subscript nu here. If I did that, then what we would do is to introduce the number density of the photons. Number density of photons. We now couple this number density of the photons with the energy density. So, how do we do that? Each photon carries an energy h nu. So, let us write that down. Each photon carries an energy h nu. Therefore, n photons per unit volume carry an energy n h nu. Therefore, U is equal to n h nu. That is what we have. But then, since this is given by pi c, so I will put a subscript nu here, I will put a subscript nu here. This is the energy density associated with that particular frequency. What do we conclude? We conclude that pi nu, if you look at this, is nothing but nh nu by c. That is what I am going to get. So, and nu by c is nothing but what we are going to get regarding lambda. So, let us remember c equal to nu lambda is what I have. Therefore, nu by c is nothing but 1 over lambda, which is nh by lambda. Remember, n is the number density associated with the photons, so many photons. So, there is a natural interpretation for this h by lambda. So, we say that h by lambda is the momentum carried by each photon. H by lambda is the momentum carried by each photon. Therefore, the Planck hypothesis not only associates an energy with a frequency, it also associates with a momentum with the frequency, or for that matter the wavelength, and this is exactly what de Broglie employed even in the case of massive particles. That is what he did. This is essentially a very short summary of whatever we covered in the previous lecture. However, when it comes to matter waves, there is a complication, and that is something that we have to remember. We have a number of expressions. So, what I will do is I will look at matter. So, let us say electron. So, here I look at it from the viewpoint of a particle, and here I look at it from the viewpoint of a wave. Let us try to understand that. Now, from the viewpoint of a particle, my energy is given by p squared over 2m, where p is the momentum of the particle, so which is also equal to half mv squared. So, the relation between energy and momentum is given by E equal to p squared by 2m, and my momentum is of course mv. So, these relations I will call NR. NR is Newtonian relation or non-relativistic relation. Of course, somebody may say, why are you using this? Use the more exact expression for energy and momentum coming from relativity. All of you are familiar with the expression for relativistic energy, mass defect. In fact, we are also going to discuss that in the next few lectures, after a few lectures. So, there I would write E equal to mc squared over root of 1 minus v squared by c squared, and p is equal to mv over root of 1 minus v squared by c squared. These are the expressions, and this I will call ER, coming from Einstein's relativity. So, these are the Einstein relations, these are the Newtonian relations. What about the wave? Whether it is a relativistic particle or a non-relativistic particle, the Planck hypothesis and the de Broglie wave hypothesis does not change. That is a very important thing. So, for both of them we have a common formula, E equal to h nu and P equal to h by lambda. But the point is that the minute you give me E and P, you are giving me nu and lambda, therefore, I should be able to immediately write an expression for the velocity. So, here the v is the velocity of the particle, particle speed let us say, whereas here my v wave can be written as nu into lambda. And what is nu into lambda? That is E by h, and lambda is h by p, which is E by p. When it comes to light, it is of no matter to worry, because we started with the relation E equal to Pc, but now we see we are going to have a problem with the particle picture, because whether you make use of the non-relativistic formula or the relativistic formula, you are going to get a different expression for the velocities. Let me write that down again. We found that v wave is equal to nu lambda is nothing but E by p. This is dimensionally correct, there is no problem about it. Now what we shall do is to write v particle both in the case of non-relativistic relation and the relativistic relation. So, in the non-relativistic relation, my v is simply given by p by m if you want, and that is it. You do not have to express it in terms of energy, but v is simply given by p by m, and in the relativistic case, v of the particle in the relativistic case will be slightly different. So, I will have to work that out. Let me show you the thing again. So, what I will do is I will multiply p by c squared and divide by E. That is what I am going to do. So, this is nothing but p into c squared divided by E, which has the correct definition of speed, dimension of speed. Because please remember, E by p itself was speed, p by E is 1 over speed, speed squared divided by speed is this. These are the expressions that we are going to get. Now clearly, p by m is not equal to E by p, nor is pc squared by E equal to E by p, unless E equal to pc, and E equal to pc is valid only for radiation or for particles which do not have a rest mass. That means there is a discrepancy. This is something that we had not encountered earlier. So, let us write a relation statement. It appears as if the wave associated with the electron and the particle associated with the electron move with different speeds. This is certainly of concern, but not of very great concern. Anyway, to round up the discussion, I can tell you what the wave velocity will be. My wave velocity will be particle velocity divided by 2 for non-relativistic case, and this will be c squared by v for relativistic case. You can work that out because I have written all the, and both of them are going to land us in trouble. So, how would we answer this? Is the concept of a wave wrong, or is it that we have made a mistake? The answer is that the definition of velocity is a rather delicate one, and later when you go for higher studies in physics, when you study wave phenomena, you will realize that velocity is given by the speed with which some information is carried, and we would have to replace the definition. What is the definition that we had? V equal to nu lambda. This V is what is called as the phase velocity. That has to be replaced by a more rigorous definition, more accurate definition called the group velocity. You will learn that, but at this point you should know that we should not naively use all the formulae available at our disposal. Sometimes it works, sometimes it does not work. I am not going to spend any time on introducing the concept of group velocity for you. That is possible to do that by looking at the superposition of two waves whose frequencies are very close to each other, but let us not digress. So, this should conclude our discussion of the matter waves. We know that our matter waves carry an energy, they carry a frequency, and then of course they propagate with a certain velocity, and as I told you, if you do a careful calculation, that will agree with the particle velocity. But then, as always, we should remember that the relation exactly between the particle and the wave is not clear. De Broglie himself imagined that every particle was associated with a wave, and the particle used to sit somewhere here and it would ride along with the wave, and he called them pilot waves. So, this was the de Broglie way of imagining matter waves, but then today one does not subscribe to this viewpoint, except probably for a very, very small minority of physicists, because all these ideas get replaced by the concept of what is called as a wave function or a probability amplitude, which again you will study in your higher classes. So, let us conclude the discussion on matter waves, and let us move on to discuss the structure of the atom. If there are two things that have attracted the attention of humankind, all thinkers have thought about it. One is the nature of our universe, how big it is and what its structure, what we call as the large scale structure of the universe, and other is the ultimate constituents of matter. So, now what I am going to do is to show you a number of slides to give you an idea of how the atom concept has evolved over centuries, in fact over millennia, thousands of years, and how in 17th, 18th, 19th century contributions from physicists, chemists, engineers, in fact thermodynamics people actually contributed to sharpen our idea of an atom. So, let us look at the next slide. Now, as to what the ultimate constituents of matter are hinges on the question whether matter is continuous or whether matter is discrete. So, it is the age old question. If I look at a smooth surface, or if I look at the distribution of air in the atmosphere, or if I look at the flow of water or any fluid, they appear to be continuous. All solids appear to be continuous. Therefore, what is it that would happen if I took a microscope and started looking at minute and minute, more and more minute parts? That is a question that we have to ask. It is true that matter appears to be continuous to us, except when we join them or except when two very big units may be joined. But it is also true that this continuous distribution of matter, apparent continuous distribution of matter, actually is not absolutely continuous in the sense that you can break it. Of course, the important observation that we have to make is that you take any piece of matter, and as you start breaking it to tinier and tinier pieces, the energy that is required to break that keeps on increasing. Therefore, in the classical language, the way our ancient geniuses thought about it, one good question that one could ask is, as I keep on breaking, is it possible that I will reach an ultimate limit which is impossible to be broken? That means you should imagine that ultimate constituent to be essentially a perfectly hard sphere, and to break which you would require an infinite energy. In other words, it is immutable, it is unbreakable. Or the other concept is that no, it is a continuum, you can keep on going to smaller and smaller units. You may require higher and higher energy, but there may be no fundamental unit, and both of them are useful viewpoints in trying to understand whatever we observe in nature. We should remember at this point that it would be unfair on our part, in fact incorrect on our part, to pass any judgment on whatever theories the ancient physicists and philosophers might have had in light of the experimental evidence that we have today. That is a pitfall into which many of us tend to get into, that is to be avoided. So, to put it very broadly, in the ancient world, especially in India and Greece, there were two broad philosophies, not necessarily in contradiction with each other. The first philosophy, which I am indicating here, was proposed by this intellectual called Kanada, who started a school called the Vaisheshika school. We know that in India there were 6 major schools of philosophy. Oh, they can be listed actually. The first one was called Nyaya, which elucidated the logical principles. The second one is Vaisheshika, which was an atomistic theory. Then you had the Sankhya, which proposed the idea of what we call as Prakriti and Purusha, the nature and the soul. They had their own theory of the world in terms of 3 gunas or 3 attributes, what they called Sattva, Rajas and Tamas. Then there was the practical aspect of Sankhya, which came to be known as Yoga, which was propounded by Patanjali. So you have Nyaya, Vaisheshika, Sankhya, Yoga. And there are 2 schools which are completely dedicated to the interpretation of the Vedas. One was the so-called Purvamimamsa, which concentrated on the ritualistic aspect, and then the Uttaramimamsa, which concentrated on the spiritual aspects. So these schools of philosophy also gave a worldview. For example, the Purvamimamsa school believed very seriously that the universe can be neither created nor destroyed. It had to be eternal for the sake of consistency within their theory. The Purvamimamsaka school was not particularly worried about the ultimate constituents of matter, because they said that that is something that is to be decided by observation, and they need not be worried about that. The validity of their school of philosophy, that is also true of the Vedanta or the Uttaramimamsa, was quite independent of that. So, when we are speaking of the schools, we are interested obviously in the atomic school, which was propagated by Kanada, and his school of philosophy is called Vaisheshika. Vishesha is an attribute, so he attributed a number of properties to his atoms. That is why it is called as the Vaisheshika school, and they gave an elaborate theory where they assumed that all matter is composed of ultimate quanta or ultimate particles, which can be called as Anu. That is the word that was used. Interestingly, the word Kanada itself is some kind of a pun, because Kana is a very small particle, and Kanada means the one who eats small particles, small fragments or small pieces or whatever. And this school actually developed an elaborate theory where they said that two atoms can form a molecule, that was called a Dvyanu. So, let me write that down. So, let me start describing the Indian atomic school. Let me write the name in Hindi in Devanagari script, so that there is no confusion about the pronunciation. It is not Canada or some such thing, it is Kannada. So, you have atoms which were called anus, and you had a molecule which is obtained from two atoms, and they were called Dvyanus. Dvyanu, and then if three of them joined, that was called Trasarenu, so on and so forth, and they developed a theory as to what is the minimum number of atoms or anus that are required to be seen by the naked eye. Of course, in order to argue, you may empirically look at the atmosphere around you. If there is a beam of light passing, you can see very, very small particles, what we today understand as the Tyndall effect. Or if you close your eyes and press it hard, you will see some very, very small strands which are moving. So, the atomic school imagined that these are the smallest particles that can be seen, and I do not remember exactly, they probably said that what one requires is Trasarenu, a minimum of 3 molecules to be seen. There is a counterpart school which said that all matter is composed of 5 elements. In Greece it was 4 elements. And what are those 5 elements? These are earth, water, fire, air, and what we call as Akasha, loosely translated in English as ether. That is what they did. Now, we should not confuse the word earth to be the earth that we see, the word water to be the water that we use for drinking or washing or other purposes. Fire is not to be confused with the fire that is used for cooking or burning. These were representative names. Earth was supposed to signify solidity, water was supposed to signify fluidity, so on and so forth. And there was a sensory organ associated with each of them, corresponding to the sense of sight, touch, audition, hearing, taste, etc. That is what we needed, and they made an elaborate theory. And at this juncture, the theory of the 5 elements is not necessarily in contradiction with the atomic school, because it was perfectly possible that these fundamental atoms actually corresponded to the quantized version of these units of sensory perception. In a similar manner, in Greece, if you look at this slide, it was Democritus who propagated the idea of ultimate constituents of matter. So much so, he made a statement, atoms are the only real objects and everything else is a figment of imagination. And again, there was the complementary school in Greece due to Aristotle, who postulated that everything that we see in the universe is composed of the 4 elements. They let the ether out. Now, this is at the realm of the speculation, and as I told you, today we cannot actually judge either Kannada or Democritus based on the fact that an atomistic theory has been supported by modern experiments, because the atoms that they had in mind were completely different from the atoms that we are going to discuss today. In a similar manner, the concept of a graha in Indian astronomy, for example, is completely different from the concept of a planet that we have today. Therefore, we should not rush to draw conclusions by saying, oh, the ancient mathematicians, ancient astronomers, ancient philosophers already knew whatever we are doing today, or to jump to the conclusion they did not know what we are doing today, because the language and the purport or the purpose are quite different. What we should gain by looking at our history, the ancient history of all civilizations, is to see how sharp the intellect was, how good the reasoning was. That is what we should put to good use when we study science, and that is very, very precious. That is something that we have to remember. In fact, you saw evidence for that in your course on gravitation, when we saw how people were very able to intelligently estimate distances and size of astrophysical objects. Now, obviously all these ideas remained as undercurrents, but once the medieval period started, after the Renaissance started and experiments in chemistry and mechanics started, Newton actually reignited this discussion, and apart from his great Principia Mathematica, where he gave the 3 laws of motion and also the law of gravitation, Newton has written a very important book called the Optic, O-P-T-I-K, Optic, where he described all his experiments on light, starting with the experiment on prism, the resolution of 7 colors, dispersion, and then of course reflection, refraction, so on and so forth. In fact, Newton even tried to measure the speed of light, but he could not, and therefore he concluded that the distances and clocks that they had were not good enough to measure the speed of light. He did not necessarily believe that the speed of light is infinite. Then of course came the chemists, who started looking at the chemical processes, and then they were able to make a great distinction, a very important distinction between a molecule and an element, rather a compound and an element. And thanks to Dalton all the way up to Mendeleev, people were able to write down the periodic table where they had about, let us say, 80 to 90 elements starting with hydrogen, and much of the chemistry could be understood. Now, if you go through the periodic table, which you will certainly go through in your chemistry course, you can move along the row or you can move along the column. You will see that there is a very definite pattern, the way in which the chemical properties behave, and therefore it became extraordinarily tempting to actually assume that all these elements are composed of fundamental objects called atoms, and the constituents of atoms themselves must be the same for all these elements. That was the great idea. Meanwhile, experiments had, on the other direction, had already shown the existence of electrons to the cathode rays. They had shown the existence of the protons through radioactive decay or other observations, the other radioactive observations. So one wanted to tie whatever we saw in the cathode ray experiments, whatever came from chemistry, and of course the great idea of Newton that probably there are very small objects which are infinitely strong. That was the thing. So what we are going to say is that one had a rather vague idea of what an atom is, but now we are in a position to actually define that very precisely. So again, if you look at this slide, you see these are the great names which contributed to actually sharpening the concept of an atom. Priestley, who actually got hydrogen for the first time; Lavoisier, who was able to isolate oxygen; then of course Dalton and Mendeleev, who get the periodic table. And from the radioactive side, we have the great couple, Marie and Pierre Curie, who actually did a number of studies on radioactive materials to the detriment of their own health, and Becquerel, who actually discovered radioactivity. All these allow us to actually formulate the concept of atom. So now today when I speak of an atom, I do not speak of an object which is infinitely strong or a hard sphere. We shall now define atom as, which I am showing in this slide. Atoms are fundamental units of chemical reaction, that is, they are ultimate constituents of elements. What do I mean by ultimate? Ultimate to the extent that I am studying a chemical reaction. There can be some other reaction. For example, radioactive decay cannot be understood in terms of chemical reactions, cannot be classified as a chemical reaction. Although Marie Curie, probably Pierre Curie also, got a Nobel Prize in chemistry. Those days there was no great distinction between physics and chemistry. And one important consequence is that when we say that they are fundamental units of chemical reaction, they may be or they may not be ultimate constituents of matter. At this point, we should also remember that thermodynamics gave a very great push to the concept of an atom. Boltzmann made his great molecular hypothesis and developed kinetic theory, from which, for example, the thermodynamic relations, ideal gas equations, etc. could be understood. So a confluence, a coming together of all these ideas from thermodynamics, from chemistry, from physics, give rise to the concept of an atom, and these atoms are for real. And what is the fundamental question that we have at our disposal? What is the structure of the atom? So this long introduction brings us to the main question that we have. And here is a cartoon which is probably picked up from Encyclopedia Britannica, which gives you what the concept is. Please remember that people had seen alpha particles, but then they were not able to measure what their sizes are, etc., etc. So there are two major contenders. One is the so-called plum pudding model due to Thomson, and another is planetary model. I am afraid that there is a typing error here, that P should be missing. Even if P were there, it would be silent, but in any case P should be missing, and the planetary model due to Rutherford. The plum pudding model, which I will come to in a minute, was just a model. It had no experimental basis, whereas the planetary model of Rutherford was forced by experiment, and obviously there is no wonder that this is what we are going to advocate and we are going to give support to in the rest of the course. Let us remember that. So if you look at the first figure, this is the elementary primitive picture of Democritus in 460 BC, Dalton in 1803 AD, probably Kanada was also somewhere in 200 BC or whatever, I do not know the age. Okay. So they imagined very, very hard spheres. Then came all the experimental developments, as we said. So we jump, let us say, from 460 BC to 1900. So we are speaking of 2500 years. You have the Thomson model. In the Thomson model, what is happening is that this is my full atom. Is that okay? Of about 10 to the power of minus 10 meters, 0.1 nanometers. And the blue haze that you see all throughout is the uniform distribution of positive charges, and the yellow small bullet like things that you see are the electrons. So the uniform positive charge distribution adds up to a total charge Q. Then there are these n electrons whose total charge also adds to Q with the opposite sign, and the atom is overall stable. This is the Thomson model. Actually, this model can be tested on grounds of stability, because one knows that in electrostatics it is impossible to have a stable configuration of charges. That means atom would not be stable. Then you would have to assume a more complicated model where all these electrons are probably moving within the positive soup. That is why it is called the plum and the pudding model. Is that okay? So electrons are like plums which are there in the pudding. Okay, and probably there is a certain flow of current because of the positive charges themselves, but we do not have any information on the details of this model. Here comes the Rutherford model, which shows that all the positive charge is concentrated in this purple center, which is a very, very small region compared to the total size of the atom. In fact, this is not to the scale, because we will see that the nucleus where the positive charge is all concentrated is 10,000 times smaller than the atom. So we are speaking of something like 1 centimeter and 100 kilometers or some such thing. So we cannot even plot it in a figure like this. So it is highly exaggerated. These are illustrations. Then of course there is a Bohr theory which resembles this, but it is much more complicated. It is sufficient to look at these two figures, and we have to decide whether which of the two are correct. And this is the experiment which Rutherford undertook in order to settle the matter. It is not that Rutherford disbelieved the plum pudding model. It is thus that he wanted to verify. In fact, nobody thought of a planetary model, because as we shall see, planetary model, although it gets an excellent confirmation from the Rutherford experiment, gives rise to other problems which people were already aware of. It can explain the Rutherford experiment, but it cannot explain the stability of the atom, and atoms have been there for billions of years, many billions of years. That is something we have to worry about. So we are interested in the experiment of the Rutherford, and this again is a picture taken from the Encyclopedia Britannica that is written here, and this illustrates very well what Rutherford did. So probably I should describe this and then go to the experimental detail. So he took a radioactive source which was nothing but bismuth. Bismuth has an atomic weight of 214 and an atomic number 83. That means it has 83 electrons, 83 protons in our modern language, and the rest are all neutrons. And bismuth decays by radioactivity and it emits alpha particles. And alpha particles carry 2 units of charge and 4 units of mass. It is essentially helium nucleus. That means it is made up of 2 protons and 2 electrons, and they come up with a rather large energy. The energy is about 5.5 million electron volt. This number is very important for us, because in an atom, later when you do Bohr model or even when you look at the spectroscopic data, all energies are in the electron volt range or a fraction of an electron volt. So we are speaking of energies which are 10 to the power of 6 times larger than the energies associated with the atom. Now what was the target? The target was a very thin gold foil. In fact, it had a thickness of 2.1 into 10 to the power of minus 7 meters, and that means it had only very few layers of atoms. That is a very important thing. It was not a thick target where my alpha particle could actually undergo multiple scattering. That was an unlikely event. Now, what Rutherford used in his experiment was a zinc sulfide detector, which is essentially scintillation. So what we are saying is that the alpha particle gets scattered off by a gold atom. Alpha particles have come from bismuth, okay? They get scattered off and they go and hit this zinc sulfide target, and every time they hit, there is a scintillation counter. So what you do is to take a microscope, look at scintillation, count the number of scintillations. That will give you the number of alpha particles that have been scattered at an angle. So with this description, let us go back and look at this illustration. There is a similar illustration which is there in your textbook also. This is a little bit more colorful. So what you have is a radioactive source here, bismuth. By this time, physicists knew the perils of radioactivity, so you have to shield yourself. So there is a nice lead shield. It must be a thick lead shield actually, probably, I don't know, of the order of even a meter or a centimeter, and this radioactive source emits alpha particles. This experiment is delicate and requires care, because radioactivity is a completely statistical process. You cannot know, unpredictable process. You do not know when the next decay will take place. You can only assign probability. That is something that you will study when you study radioactivity. It is completely probabilistic. So when this bismuth nucleus decays by emission of an alpha particle, there is a small hole made here and the alpha particles come through, but then you want as narrow a beam as possible. So what you do, you put one more lead sheet and you make an even more small beam which collimates, and this comes and goes and hits or impinges on this yellow sheet, which is nothing but the gold foil. That is why it is going to show gold color, and then the atom starts getting scattered. Now these are representations of the zinc sulfide crystal, and you can see that these zinc sulfide sheets, they can move along. Unfortunately, this illustration is not very true to the experiment. This lead shield cannot be this big, it should be much smaller, because the zinc sulfide detectors could be actually moved very close to 180 degrees, very close to the beam direction. In other words, Rutherford endeavored to cover all of 180 degrees, coming from this direction to this direction. We say 180 degrees and not 360 degrees, because by symmetry, the probability for alpha particle getting scattered in this direction is the same as probability getting scattered in this direction for the same angle theta. That is what we have, and these are the movable fluorescent screens. That is the experiment, and this is a representation of the experimental result. We find that particles which are moving farther away, very far away, are probably not getting scattered at all, far away from the atom, whereas particles which are moving very close to the center of the atom are getting back scattered. I am going to discuss this experimental result in great detail, because as I told you, this is one of the defining experiments in the history of physics, like Galileo's observation of craters of moon or moons of Jupiter, or for that matter the observation of Halley's comet, etc., or Michelson-Morley experiment. This is one of the defining experiments, and let us see therefore what the import is. Okay. These are the experimental results. I want you to present these experimental results and then go back to analysis of this experiment. Okay. First, caution: This is not exactly Rutherford experiment, but a different version, but the results are qualitatively the same and therefore they are equally good in analysis. Here you are not using helium alpha particle, but you are using proton itself, which is 2 MeV, therefore lesser mass and also lesser energy, that is what you have, and you are scattering the hydrogen nucleus against gold, this is against P phosphorus and this is against boron. All of them show the same qualitative feature, that is very, very important. On the x axis is the scattering angle or the recoil angle, which I am going to write in a minute. You start with 0, that means absolutely no scattering at all, almost no scattering, that is called the forward scattering. As you keep on increasing the angle, you are looking at the hydrogen nucleus or the hydrogen ion getting more and more scattered, and when you reach something like 180 degrees, the electrons actually, sorry, not the electrons, the hydrogen nuclei retrace their path, and this is the differential cross section. The cross section is maximum in forward scattering. It starts decreasing as you keep on increasing the angle of cross section. And what is a cross section? Angle of scattering. What is a cross section? For our purposes, cross section is essentially the number of particles that come in a given angle. Of course, this number must obviously be the fraction of the particles that are coming at a given angle. What is important is that for us is that although this is going to be smaller and smaller, this is not going to 0, that is very, very important for us, but it is saturating at some finite value, and that is something which is very important for us. So, this figure is something that we have to understand. So, what were the important features, whatever I told you there? So, I have made a mistake in typing this, I am very sorry about it. Most of the alpha particles are unscattered, they just pass through undeflected, and the number of alpha particles getting back scattered is relatively quite large, and this is going to be a problematic issue for us in order to interpret. Again, I am repeating, this must not be an electron, it must be an alpha particle in both the lines. So, please pay attention to that. Okay. Now, let us get back to do some hard analysis. Analysis of the Rutherford experiment. So, let us make a crude picture of an atom. So, this solid line denotes positive charge. So, positive charge is distributed here, and all dashed lines denote electrons. That is what we have. Thomson would say that all the electrons are inside, but without being prejudiced, we will put some of the electrons inside, some of the electrons outside, and we will see what Rutherford experiment would have to say. That is very important for us. Now, if you look at some numbers, mass of the electron is 0.5 MeV by c squared. So, when we do atomic physics, it is not convenient to use SI units, it is convenient to use atomic units and the relevant ones. So, it is good to use 0.5 MeV by c squared. If you really want to convert it into ordinary units, you know how to go from electron volt to joule, so you can do that. Whereas, mass of the alpha particle is 4 GeV by c squared. Let me remind you, 1 MeV is 10 to the power of 6 electron volt, and 1 GeV is 10 to the power of 9 electron volts. So, what are we saying? We are saying that the ratio of the mass of the electron to the mass of the alpha particle is what we are looking at, is essentially 0.5 into 10 to the power of 6 divided by 4 into 10 to the power of 9, so which is 10 to the power of minus 4, let us say. That is what we have. So that means my electron, actually I can write a precise number, is 8000 times lighter than the alpha particle. That is the statement that we are making. So it is actually equal to 1 over 8000. So if I think of a scattering of an electron and an alpha particle, that is, if I imagine that the alpha particle goes and hits an electron, it is almost as if a huge truck is going to go and hit a small brick or a ball, and that means the truck will continue to move with the same speed, but the balls will all get scattered and it will hardly affect the motion of the truck. Or another example which one of my colleagues gave is that of a ball and a small number of pins. Suppose you put a number of very, very small pins and you throw your ball. What is going to happen? If the ball is very heavy and the pins are all very, very light, the pins will all go helter-skelter. But the ball will continue to move along its direction without any appreciable change in their velocity. That means in the scattering, if at all there is a change in the angle, that is the momentum of the alpha particle, that should come because of the positive charges. So all scattering is essentially due to the positive charges. That is very, very important. So for all future purposes, we are going to ignore electrons. Maybe some of the electrons got hit badly and they flew away. We are not worried about that. However, what is important for us is to know that the detector should be able to make a distinction between the alpha particle and the electron, because the electron could also cause a fluorescence, but zinc sulfide was so chosen that it will be sensitive to the alpha particle and not the electrons that might be hitting the shield, hitting the detector. So detector is important, otherwise we may get false counts. Now let us assume that all the positive charges are distributed over a distance r. So this is a sphere and this distance is r. So when I am making this picture, I am not making any particular assumption. So I can always draw a sphere which will enclose all the positive charges, whether it is continuous or discrete, and this r is the minimum radius, sphere of the minimum radius which will enclose all the positive charges. So now what I am imagining is that there is an alpha particle which is coming towards this nucleus or this atom. Let us come to that. What should be the maximum r? R cannot be greater than the size of the atom. Greater than the size of the atom. And what is the size of the atom? Atom size is of the order of 10 to the power of minus 10 meters. So if at all the positive charge is distributed, it should be r is less than or equal to 10 to the power of minus 10 meters. Let us assume a positive distribution and let us ask what is it that happens to the alpha particle. So I have a spherically symmetric distribution. And my alpha particle is coming with an energy E equal to 5.5 MeV. we can now crudely estimate, not very crudely, approximately estimate what is the minimum distance that this alpha particle can approach vis-a-vis the nucleus with positive charge. So, you have a positive charge plus Z, which is equal to 87. Gold has an atomic number 87 and this has a positive charge Q is equal to plus 2. So, alpha particle carries 2 units of charge, the gold atoms carry 87 units of charge, like charges repel, and therefore, there is going to be a barrier. So, what we are asking is, what is the minimum distance of approach before it gets turned back? That is the question that we are asking. So, that is very easy to compute. What will I do? I will write 87 into 2 into E squared over 4 pi epsilon naught R minimum. This is the minimum distance of approach, must be equal to the energy of the alpha particle, which is 5.5 MeV is the energy. This is what we are going to equate. So, we are essentially equating the kinetic energy of the alpha particles with the potential energy. When they both become equal, then the kinetic energy, at infinity the total energy is 5.5 MeV. When all of it becomes potential energy, then the alpha particle would have to trace its path back. So, what we have is the distance of minimum distance of approach is nothing but 87 into 2 into E squared over 4 pi epsilon naught into 5.5 MeV. That is what I have. Now, what we have to do is to actually look at this and ask what is its relation vis-a-vis R, and then we have to worry about what the structure of the atom should be, and that we will take up in the next class. So, I ask all of you to work this out and verify this is of the order of 10 to the power of minus 14 meters. This is a very important number for us, and we will continue our study in the next lecture.